Hello. Today we will talk about the advantages of using automatic flow disturbance corrections. This feature makes sufficient straight lengths almost meaningless, and installations can be done on the most convenient spot regardless of piping, especially for clamp-on meters, which are still used as a retrofit or for measurement points or replacements of existing flow meters. Sufficient straight lengths are rarely available. The automatic disturbance correction provides accurate readings even under unfavorable pipings. Literally speaking, clamp-on flow meters can be installed wherever you need a measurement. We will start with the measurement principle to tell you where does actually the disturbance influence comes from and affects our flow reading. We will talk about how the automatic disturbance correction work in the following slides, what is required for installation, and what available products do I basically have, and what can I do with existing products, how can I benefit from that function. And in the end, I will give some advices or some help to analyze the measurement deviation you may face in the field when you do measurements. So how does this disturbance correction actually help us to give a better analysis of our measured data? Maybe some of you might not know FLEXIM or never heard of FLEXIM before. FLEXIM is a clamp-on manufacturer for ultrasonic flow meters. FLEXIM develops, sells, produces those flow meters. FLEXIM does it for 30 years already. It wasn't founded in the 1990s. And yeah, all shareholders are founders of the company. And they are still working here in our company, here in Berlin, in the headquarters. Most of them working in the R&D. One is the general manager. We can basically say that FLEXIM is a technology-driven company, and the development is technology-driven. Basically, that's what we call us, a global company. We serve customers worldwide in almost every branch you can imagine of. That means wherever you find a pipe, either it's a gas inside or a liquid, you can basically measure that with a fleximeter. For us, it's important and important for the customers that we have not only the products that we're gonna sell, also the service and support that, as well as our reps do and follow the same strategy. We have about 500 direct FLEXIM employees worldwide and many, many more regional sales partners and service partners around the globe. The measurement principle, for those who are not familiar with it, it's a transit time difference method. That means we clamp on our transducers from the outside of the pipe. We send a signal upstream and downstream with the flow. And when there is flow, the signals show two different travel times. And we basically measure the time difference of both signals, upstream and downstream. Multiplied with the pipe cross section area, we getting the volume flow. The formula will come later on in the slides 2 times again, so we're going to talk about it and what are the effects in the following slides. Flow profile correction. So when we talk about disturbance influences to our meter, we basically look at our K Reynolds, our compensation of the flow profile. So what we basically measure when we send a signal, we measure with the transducers the average flow velocity along our path. But what we need to know is basically the average flow velocity in the pipe. That means we need to compensate, to correct that measured value with a correction factor called K Reynolds. We need that because the flow in the pipe may look differently. We have laminar flow when we have small pipes, high viscosities, or when the flow is very slow. We have the laminar regime, then we have the transition range where it changes from laminar to turbulent flow, and the turbulent flow differs depending on the Reynolds number, and it's also part or influenced by the roughness of the pipe. So when we have a disturbed flow profile, like a 90-degree elbow, for example, as the top left picture shows here, we have a disturbed flow profile. That means our assumed flow profile for an undisturbed axial symmetric flow profile is not the case anymore because of the disturbance caused, for example, by the 90-degree elbow. In that case, our K Reynolds has an error, and the disturbance correction basically compensates that error. That's basically what we do here with our automatic disturbance correction. We compensate the error of known flow disturbances. And the grade of the disturbance depends on the straight length, right? When we have enough straight lengths, we have a fully developed flow profile again. If we do not have enough straight lengths, then we have to deal with a disturbed flow profile again. And the question always is in the field, what is basically enough straight lengths to have an undisturbed flow profile, and what is the disturbance actually? When does it take place? That's really difficult to define in the field, and that shouldn't be the question when someone installs a flow meter, because those people, they should select the most convenient, the most best spot on the pipe, definitely with the best straight length they can have, which is achievable in this on site, but it's quite difficult to find a spot which provides an undisturbed flow profile. And here our automatic flow disturbance correction comes into the game, which compensates those effects. That means it's not part of the user anymore to decide what might be the effect to the flow profile or to my reading. That's done automatically. The only thing that has to be done is measuring the distance. How that works will be followed or shown on the following slides. So here are some examples what flow profiles may look like. We have quite an extreme example. That's a double bend out of plane. Extreme because it causes a swirl as well, but not extreme in a way that we don't find it very often. That's quite a common flow profile disturbance we find in the field. That means after such a flow disturbance, flow element, the double bend out of plane in that case, we have a swirl, and the turbulences, the disturbance, is in the fluid for quite a long time. What can we do in the field? Well, inline meters, especially custody transfer meters, they normally have something like a flow conditioner. They look for the highest accuracy they can get. They have the advantage of having a flow conditioner, where the FLEXIM clamp-on meter for the process industry, for process measurements, normally does not have the advantages of having a flow conditioner in the pipe. That means we have to take the application as it is, and we normally install, in case of a retrofit, measurements where a flow meter was never be considered to be installed on that pipe. That means in such case, having undisturbed flow profile is almost never the case, because they keep it short on the distances, and we have to install flow meters where we have maybe just enough time to make the installation by itself, so that there is enough straight lengths. That's quite rarely. That means most of our installations have to deal with a disturbed flow profile, and the question is, how accurate basically is my measurement when I have to install it like that? That's a question people are always faced when installing flow meters. We give those people now an answer with our function. So what did we actually do? Years ago, we started tests about flow profile effects to clamp-on flow meters with the PTB. For those who are not familiar with the PTB is the highest German meteorological authority that we have here in Germany, and is directly subordinated to the German Department of Commerce. That means they set the standard for our flow meters, as well as for all other meteorological units we have. So we started here. They have basically, what I know, the best calibration rig you can find in Germany, because they don't care about money. They have enough money. That's why you see here the calibration rig with really nice, smooth stainless steel pipes, and they can afford it. And here we tested. We not tested only undisturbed flow profiles, we tested also different flow profiles, and those results are presented here in in the presentation, as well those results came into our product called the automatic disturbance correction. The results were recently checked here in the USA at Orden Labs. So a colleague of our FLEXIM company in New York went there last week and tested those results from the PTB here in a different lab, means different pipes, not that smooth, quite rough carbon steel pipes, different roughnesses they tested, different inlet conditions they tested, and basically it turned out that what we tested with the PTB were able to be proved here on that lab at Orden Labs as well. That means we got the same results and different pipes, and that basically proved again that what we developed works in the field. So not only the experience we already encountered in the field and gathered in the field were proved, also the whole system as we do it is proved in that way. So what is basically the output of those project with the PTB, which is still going on. So it's not finished. It's quite a long project going on for years and will continue for some more time. The result is actually a correction factor for the flow disturbances called KD. What's new in that case is that we developed that in a way that this KD only depends on the distance to the disturbance and is independent on the Reynolds number. That means that works for any pipe size and it works for any flow velocity as long as we are in turbulent regime. What do we do as a user? We make the installation on the pipe with the best installation spot we can find. And even though it's shown here that we install, on that picture, that we install the transducers in the same plane as the 90-degree elbow, for us, it doesn't matter where we install it in which plane. So that's taken into account that you can install it in any plane, because sometimes you don't have access to all of those planes, and especially not to the best one. That's why we do not say which is the best one. Install it as you can. And according to all other restrictions or recommendations for the installation. And what you do is basically just measure the distance, C, from the middle of the transducers to the end of the disturbance. That means the straight length that is available, that what you enter, or that what you measure and enter in the setup. So that means it becomes part of the setup, is stored and used. The flow meter basically calculates automatically the inner diameter, calculates it to the diameter that we have in straight length, that we far away from the disturbance, and use that in the formula and corrects basically the disturbance automatically based on the results from the PTB. So at the moment, FLEXIM introduced that one for the 90-degree band. That was the first disturbance we were able to implement. Other disturbances will follow in the near future. 90-degree bands have different bending radius. If you look into the standard, there is an ESMA standard 16.8 and an European standard forward. It defines that basically most bending radius have a bending are between 1.3 and 1.5. So that's defined, and that's optimized correction factor for those bending radius. If you have a different bending radius, you still can use it. The correction factor is the same. The only thing we have to deal with when having a different bending radius than this one, that our uncertainty calculation has to take into account a higher uncertainty when not having exactly that bending radius. But what does it mean with the uncertainty will come in the last slide I'm going to show today. For those who never heard that FLEXIM offers a solution or the possibility to make a customized uncertainty report. This disturbance correction is part of that, and I will show you how that may look like. So what is the installation requirement? We have to install it in reflect mode when having a single channel meter, or if you have a dual channel meter, you can use one of those installations as an X mode, that's what we call it, or a displaced X mode installation. Some people call it a V mode, both means the same. Why do we have to use it that way? Because Some of you might know, others might not. We have something like called cross-flow effects. Cross-flow effects is basically a flow velocity vector which is not parallel to the pipe, it's off of it, and cross-flows can never be predicted. They depend on the pipe, on the disturbance, and even sometimes on the, or not sometimes, always also on the flow velocity, so they may vary. That's why it cannot be really corrected at the same time. That needs to be done, compensated by a recommended installation, which is in the easiest way, a reflect mode installation. Most installations are done like that because it's the easiest way of installing a transducer. Or if it's not possible having a reflect mode installation due to the application influences, then a dual channel meter is to be used. In that case, you can use the disturbance correction um, as an option and compensate for it. In case if you have a single channel meter and have to install it in direct mode, you can't use the disturbance correction because that meter is affected by the cross flow effects, and that means the disturbance correction cannot be used because it doesn't make sense, because cross flow effects can be higher as an influence than what we actually correct by the disturbance correction. And that's why it doesn't make sense. It may even go in the wrong direction when compensating it. That's why it cannot be used for single channel meters in direct mode or other uneven number of sound paths like 3 or 5 sound paths. If you want to install it like that, the flow meter will basically tell you cannot be used. You have to go on without the disturbance correction. Where is it available? We introduced that product last year, and for all new products, for all products you just bought or purchased from us, it's available. If you want to know if it's really available, then look in the firmware version. If it's a new platform, it's 7.28. If it's an old platform, it's a 6, like the portable meter, it's a 6.42 firmware version. What to do with existing flow meters? Well, make a firmware update. If you make a firmware update, you will profit from that disturbance correction because then it will be available. So it can be used for older meters as well. Does it make sense for already installed meters? Probably not, because you don't want to change it. Customers or users are used to what they're reading. You can, if you want to make it better, more precise, possible. But from my point of view, basically it's the firmware update necessary for portable meters where it really makes sense to use that function. So why do I state having improved analysis on measurement deviations? So what is basically the benefit when knowing the disturbance correction? Well, knowing the influence of the disturbed flow profile brings the analysis of the measured data to a new level. Why is it that way? Because when we look at the formula, we see here delta T divided by 2 times the fluid. That's basically our time measurement coming from the transmitter. The transmitter is factory calibrated, written on a nice certificate what the uncertainty is, and once in a while, at least what we recommend every 5 years, portable meters should be calibrated more often if you use them a lot, especially when different people use the meter. So make sure that your meter is still measuring correct once in a while. The same with the transducers, K alpha, that describes our transducers. Transducers are also factory calibrated, should be calibrated, especially the portable ones, once in a while. And when knowing the flow profile, that's depending on the inlet conditions. We know the flow profile now. We know what we have the distance. We know the effect. That means we know the error, which is compensated. That means these 3 factors, at least in our flow volume, flow formula, are known. That means uncertainties are very low. That means what's left is the pipe geometry. That needs to be measured in the field because the clamp-on meter becomes a flow meter when it's installed in the field and not before. What you can do to keep that uncertainty low? Well, you measure the circumference, the bore thickness, then you know the inner diameter. So if all these factors are known, the volume flow must be correct. And if you see a difference now to the meter you want to compare with, means if you use the FLEXIM meter as a check meter, then you know there is maybe the meter wrong reading of the meter you compare with. That's what we basically can state. Or maybe the pipe isn't that well known. You measure the circumference, well, that's okay. You measure the pipe, wall thickness. That's also quite, yeah, sure, and you can make sure that that is correct. But what about build-ups? So, well, some either diagnostics might tell you that there is a build-up or some influences in the pipe wall, but what's left, and if you still see a high reading, you may need to consider that you may have build-ups, and that is something you can narrow down. That means um, knowing the flow profile tells us that everything which is left in uncertainty or as an error must come from the pipe geometry or build-ups or things like that. Or it points out that the meter you compare with is probably wrong. That's what you basically can do. Before, it was always difficult to say, well, we have maybe build-ups, maybe the build-up is the problem why we measuring off. We don't know what the influence of the disturbance is. Since we know the disturbance, we can eliminate that factor and bring down the problem to the real influence, what we see on site. So what's also possible, here is an example of a special solution we did for a customer here in Europe. It's a gas customer here at the dosing station, and he always has the same piping for all the dosing stations, and he wanted to have the best accurate reading. So what we just did was testing it on one single pipe and defined the correction factors. And then we had the correction factor for all other pipe sizes as well, because the correction factor we defined is independent of the Reynolds number. That means as well it is independent on the pipe size and independent of the flow velocity. That means it can be used on any piping which looks basically the same, which is the same inlet conditions. This correction factor works on all of his dosing stations. So that's what he basically does. And that's one output from the PTB test, that once you have a disturbance correction for a specific disturbance, you can use it on any pipe size, on any fluids, either gas or liquids, for any flow velocities, as long as you are in a tolerant flow regime. It applies for all of those at the same time. So, measurement uncertainty, as I said, for those who are not familiar with the FLEXIM software, you are able to calculate uncertainty or make an uncertainty calculation for each specific customized uncertainty calculation specifically for that application you're dealing with. You enter the diameter, wall thicknesses, how you measured it, transducers you select, the installation you select, and it will pops up with an uncertainty when you have calibrated systems. It comes into account that, or it can be taken into account that we have a disturbance correction. So if you switch that on, select your disturbance type, enter the distance, the correction factor is used in the background. And this correction factor basically has an additional uncertainty, because correction factor needs to have it. You can't have a 100% correct correction factor. That's not going to work. Each factor has an uncertainty, and that is automatically taken into account. That depends on the distance as well as on the transducer arrangement. That means a different uncertainty when having one set of transducer and a better uncertainty when using two sets of transducer. Same for 3 or 4 sets of transducers. And that's basically taken into account into our uncertainty calculation, and that what you read, assuming good diagnostics, is that what you basically get. And that's reliable, based on a standard, on the standard to define uncertainties. And that's something you really can use, show it to your boss, document it, as well as showing it to customers if you have one of those. Good. As a summary, what did we learn today? The disturbance correction improves the accuracy for installations with the disturbed flow profile. That means almost every application in the field profits from that, because you nearly have disturbed flow profiles in every application you find, as long as you have many Ds of straight lengths. The 90-degree band in the fleximeter is now included. Other disturbances will follow. If you have other disturbances, use that correction anyway, because it makes the correction in the same direction. That means disturbances either have 3 or 4 or 5%, depending on the diameter straight length. They always have created an under reading in the flow. only for longer straight lengths and for certain disturbances we have an over-reading, but mostly an under-reading. So using a disturbance correction will make the reading always more accurate than not using any disturbance correction. So even if you have something like a 90-degree error or double bend out of plane, use that function because it makes the reading better instead of not using it at all. Why? Because it's also part of the setup. So in any case, you want to check what you really compensated, you can do it later anyway and make a calculation out of it. We have an improved uncertainty report, including the disturbance correction, that's what I showed you, and you have improved documentation. As I said, the disturbance correction becomes part of the setup. That means it's documented, you can print the report, and even after years of installation, you still can check what did I actually install and used. It's documented, and as long as you do not delete the files, you have it documented forever. It's available for all Fluxus flow meters, for portable and dedicated ones. And as I said, you have an improved analysis of the measurement deviation because you can narrow down to the actual influence, because once you know all the factors, or at least 3 or 4 factors, then you can define or easily say where the deviation comes from. Before we had 2 more or less unknown factors. Now K Reynolds is defined, is known. That means you can bring it down to the real problem in the field. And that gives you the argument to do so and to find the right explanation. Good. I hope you enjoyed it. And I'm happy to answer your questions now.